Now that we're done discussing the moons, let's talk about the rings associated with the giant planets. So, the way to read this graph is that you're going to say this is the distance from the planet's surface. And remember, there are some vague definitions to the surface of a gas planet, but regardless, there is some finite range within that atmosphere that we'd call the surface. And as you get away from the surface of the planet, what types of rings are you going to find? Saturn's rings are very well defined. You get these C gaps, B's, and the A and F rings, even rings further out than that we'll talk about. Jupiter, similar pattern. It's a ring that kind of just stretches out into this nice formal band here. Now, what are these little circles? These are representations of a couple of moons of these giant planets. And the dashed line, that represents that tidal stability limit. Think back to that demo with the paperclip with it flexing and stretching. If you are too massive and you come within this tidal stability limit, what happens to you? You get tidally ripped apart. You go beyond what's called the Roche limit, and you are literally smashed into pieces. Now, this won't happen to every moon. You'll notice that there are some moons orbiting within the rings underneath this tidal stability limit. And that's just because the mass, the size of these rings are small enough, the mass and size of these moons are small enough that they don't get destroyed by tidal forces. But in general, underneath this, you're going to find rings around the giant planets. And what are they? They're tiny grains to maybe house-sized boulders floating around, rotating around their planet. Putting it in perspective again, notice how, like we said, the terrestrial planets do not have any ring systems, but the giants, every single one of them will. Saturn's being the easiest to visualize and detect, but even Jupiter, Uranus, and Neptune will have some rings associated with them. So with that, let's focus on Saturn's rings, because they are the most prevalent, most beautiful, visually stunning rings that we can discuss. So we'll shift our perspective to the south pole of Saturn and start picking out what features that we can detect in these rings. And the first thing, you notice there's a little bit of a gap, right? A region of basically no rings. But if you look carefully, you can see there's bands. These are darker bands of rings. So we talk about how there are ringlets, multiple rings stacked, layered on top of each other, going outwards. Then you get to the B ring, which has this label of 2DE. What does that mean? What it means is that this width of this B gap is so big that you could fit 2 whole Earths inside this gap. It is wide enough that 2 Earths could be stacked on top of it and still fall within the width of this gap, of this B ring. Going further out, you'll have what's called the Cassini division, where you have this gap. Right? The density has suddenly dropped off. And the Cassini division is only slightly smaller than the diameter of Mercury. There's another gap here, this Encke gap, which is a little bit smaller. And that's sandwiched in between the A ring. Now, each of these rings are composed of billions of tiny particles that are all obeying Kepler's laws. Kepler's laws saying, what their orbital velocities are. Focusing on the A and B ring, B being closer to Saturn than A, let's ask about their rotation rates or their angular velocities and say, how do the rotation rates of A compare to ring B? Go ahead and pause and think about this one for a little bit and then come back. So, what are the answers? Should A be rotating faster or less than or at the same rate as B? Well, to answer that question, first I'm going to do a little demonstration for you that's going to be the wrong answer. A lot of people are going to make assumptions and they're going to forget some of the laws that we've applied and learned in the past. So I just want to take this as an opportunity to see how we can seemingly convince ourselves of the incorrect solution. So let me emphasize. What we're going to see will lead us to the wrong conclusion, and we're going to discuss why it's wrong. So here we have two masses separated by different distances away from the center of this rotating platform. And if I just give it a little spin, let's look at their rotational velocities in this picture. Both objects are rotating in unison around their center. Let's give it a little bit faster speed. Now think of this. The one at the blue line, the outer one, it has to travel a greater distance. It has a bigger radius, a larger circumference to travel. Whereas the smaller one has only this small circumference to travel. And so while we'd say that their speeds, their tangential speeds are different. Oops. While we can say they're tangential, the speeds tangent will be different. The inner one has a lower tangential speed than the outer one. We'd say their angular speeds, their angular velocities are identical in this picture. They are rotating at the same frequency. So if we were to think in terms of this picture, we would lead to the wrong conclusion that our Saturn's rings rotate at the same rates, the same velocities. But let's cut over to our video now. Cut out of the video. Coming back to our picture here, what we actually would conclude is that the closer object must move faster. So what's the difference? What's the difference between this here of the objects rotating at the same rate versus a moon? What's the differences? We're trying to use logic. We're trying to use our intuition to build up these pictures. Well, the failure is, what's the force that generates this rotation? Come back to this picture here. As they're rotating, there must be something providing a force pointing towards the center of motion. Well, in this picture, that force would be friction. Just a little bit of friction sliding around. Well, riddle me this. The frictional force on this guy versus this one. Which one's bigger? Same force. As long as we're going at a slow enough speed, they're experiencing the same force. And by same force, I mean from here out to here. That radial force is constant. Constant force will make these things rotate at the same rate. Now let's come back to Saturn's rings. Talk about the force on B ring here versus A ring, which is going to be out here. Oops. So the radius is bigger for the A ring versus the B ring. Well, what does that mean? That means that the force here is greater force. The force is greater on the B ring than it is on the A ring. A greater force means it's going to have to rotate faster. And coming back to what was literally said on our previous slides, these particles, these rings, obey Kepler's laws. The closer you are to the object, the faster you must rotate. The force got bigger. There is this differential force. This force is spread out. Stronger here, weaker here, which leads to this conclusion that the B rings will rotate faster than the A rings. Continuing on, let's look at these distances between the surface of Saturn to the inner rings. They'll be about 7,000 kilometers, stretching out upwards of almost 80,000 kilometers away from the outer edges of the planet. And yet, look at the thickness of this. While the rings will extend almost 80,000 kilometers away from the planet, the thickness of these things is only at best, say, a kilometer. So to put this in perspective, if I was to hold up a basketball for you and put a thin little piece of paper in front of that, the comparison of this width, this 1 kilometer to 80,000 kilometers, that paper width to the basketball diameter is 1,000 times still too thick. So these rings are paper thin. Even that is too big. Wrap this up. These gaps, while they appear empty, are absolutely not. There's definitely still material floating around there. And the brightness, how bright or how dark the rings are, is indicative of what material is there. You're going to find darker, maybe some organic materials versus ices out here. Even bigger, going beyond that. Here are some pictures of the rings, and we zoom that down, shrink down here, we can still find bigger, more diffuse rings. And these are very faint, and they don't really have any defined boundaries. We only started discovering these about, at the time of this video, a decade ago. And so these are going to be hard to define layers of what these rings are, these diffuse rings.